Today we are happy to have Misha Temkin, and he will talk about his work with PHK, and the name of his talk is on numbers associated with a strong Morse function.
Right. So first of all, I want to thank the organizers for having me. It's a pleasure to speak at this seminar. So basically, I'll be talking about the joint work with PHK. It's going to be like in a few words about a single invariant of a strong Morse function, about its various properties and all that. So please interrupt me at any time should you have any questions. I would be glad to answer. So the plan is the following. So first, I'm going to set the stage, and I'm going to say how the invariant looks like. And the second part, I'm going to actually construct this invariant. The third part, I'm going to speak about its properties and a couple of examples. And the fourth part, the fifth one, will contain two main theorems on the relation of this invariant to the Dartmouth torsion. And if time permits, I will also say a few words about the parametric Morse theory and how this invariant interplays with this branch of the Morse theory. Okay, so the setup is the following. So M is a closed manifold, differentiable. F is a strong Morse function. So what I mean by strong is that all the critical points have different critical values. So the picture on the right is prohibited. So these 2 points have the same critical values. That's prohibited. So if the function is strong, then, well, it is still a generic condition in the space of all the functions on the manifold. And big F is a field in the algebraic sense, a ring with division. So the invariant takes as an input small f and a big F, so a strong Morse function and a field. And the output of this invariant is twofold. It's called the enhanced barcode. So the first part is the pairing of some critical points with neighboring indices. And second, the broad number, which we denote as lambda, on each pair. So by number, I mean the non-zero element of the field defined up to sign. So the picture of this enhanced barcode is drawn on the right. So the dots depict the points. So there's a natural linear order on the critical points because all the critical values are different. So the critical values and the critical points are in natural bijection. So that's why we draw this the critical points from bottom to top in the sense of this linear order. Right. So the pairing is drawn in this cyan color. So there are 4 pairs on this picture on the right. The brown number is drawn on in blue. So the brown numbers here are 1/6, 1, 2, and 3, and the field is say Q. Okay. Right. So I want to warn that I don't take a Riemannian metric as an input, right? So there's no Riemannian metric fixed, and hence there's no Morse complex for this function f, right? So the Morse complex only arises if the Riemannian metric is fixed, and it actually does depend on the metric, and I don't want to fix it. And the second warning is that paired points need not be neighboring in the sense of this linear order, which I've been talking about earlier, right? So for example, this pair, right? These 2 critical points are not neighboring in the natural linear order because there are many points in between them, right? So all these points are in between them, and still these 2 critical points are paired, right?
Just a basic number. So this Bruhat numbers. So since you don't fix a metric, I mean, they a priori do not depend on the metric, right?
Yeah, so I will take a function and a field as an input. So
Okay,
they
I
don't
see.
depend on the metric. Yeah, I
Right.
mean, and even during the course of the construction, I will not fix any metric.
Okay. Okay.
So the construction will be only in terms of the input, only in terms of the
Thanks.
function, right?
Okay.
So there is a way, an alternative way to define it using the Morse complex, but I can talk about it later, like in the end. Okay, right. So any questions on the setup? No? Okay, great. So the terminology here is that if the point, the upper point in the pair is called upper, and they are drawn in the red color. So these are upper points. Lower are called lower. They are drawn in purple. So these are lower points. And some points are not paired. For example, the two which are left. So these points are not paired, and the points which are not paired are called homological for the reasons which I will tell you later. So each point is one of the three types, right? So now I'm going to actually construct the output given the input, the enhanced barcode given the function and the field. Okay, right. So let me fix. So what should I do? Given two critical points, say x and y, I should tell you the condition under which they are paired, and if this condition is satisfied, I should also tell you the number, the Brown number on this pair, right? So let me do precisely this. So x and y are critical points. Index of y is k, index of x is k plus 1, and f of x is greater than f of y, right? So if this condition is not satisfied, then x and y cannot be paired a priori. So this is the necessary condition, but not sufficient, right? So the picture is on the right. So x is of index, so k is 1. So x is the critical point of x2, y is the critical point of x1. So recall the notion of a sublevel set, MA, which is defined as all the points in a manifold such that f of p is less or equal than a, and a is some real number, right? So now, what I want to do, I want to consider a topological pair. So the topological pair is just a pair of topological spaces. So a space and a subspace. So the first, the bigger element in the pair is m f of x minus epsilon, where epsilon is some small number. So schematically, this subspace is everything which is slightly below x, right? So this is the bigger element, the greater element in the pair, and the smaller element in the pair is m f of y minus epsilon. So this is everything which is below, strictly below the height of y. Okay. So I want to consider this pair of topological spaces, and then I want to consider its homology, its relative homology with coefficients in f and in degree k, where this k is exactly this k, which was here, right? So this is, after all, a vector space over f, finite dimensional, and in this vector space, I want to consider two vectors. Yeah. So this holes denote that there may be some critical points in between x and y. Yeah. So I've stated that the pair points need not be neighboring, so there may be some points in between. This is perfectly fine. So in this vector space, I want to consider two homological classes. Big X is the attaching sphere for X. So the basic theorem of the Morse theory tells you that to a critical point of index k, there corresponds a cell, an attaching cell of dimension k, So since index of x is k plus 1, it corresponds to a k plus 1 cell, which is being attached along a sphere of dimension k, right? So the dimension is exactly k, and it's drawn in purple in this picture. So if k equals 1, then I simply attach a two cell along a circle, which is drawn. So this class is essentially not relative. It is an absolute class. So it actually lives here, right? But I just want to consider it in the relative homology group just because I can. So that's the first class. And the second class is Y, which is drawn in blue. And this is the class of the attachment disk for Y. Yeah. So I take the whole cell, which is now an essentially relative homology class because its boundary is non-empty. Its boundary is k minus 1 sphere, which lives in this space. Yes. So in this case, it is zero-dimensional sphere, 2 points, which live in this subspace, right? So this class is essentially a relative one, right? So now I have two classes, two vectors in my vector space, and the definition is that two critical points x and y are paired with Brown number lambda if big X equals to lambda big Y and both are non-zero. So if these two vectors are proportional, then we say that x and y are paired, and the coefficient of proportionality of the two is exactly the Brown number, right? So two comments are in order. So first, I didn't fix any orientations. So all the classes are only defined up to multiplication by -1, depending on the orientation you choose. So that's why this lambda is also defined only up to ±1, right? As stated here. But that's a minor ambiguity. Right. So that's the first comment. Yes, and the second one is that given this definition, one has to check its correctness, right? So, for example, it is not maybe evident a priori at the first glance that each critical point belongs only to one pair. So it is a statement that each critical point after this procedure is being either paired with a single other critical point or is not paired. Okay, so it's not possible that 2 points two points are paired with a third one, right? So this is not possible. So this is a statement which is, well, an easy one. Right, so that was the definition of the enhanced barcode. And so the reference are the following. So without raw numbers, so if you just simply disregard the numbers, then it is just called the good old barcode, which was essentially defined by Morse in 39 and then discovered by Barannikov in 94, and then it became a popular tool in applied and selected topology, and it's called the persistent homology. So the definition is the Morse definition, Barannikov definition, and the definition which is used in the applied topology, they're all different, and they're all are different from the one which I have just given, but they're all equivalent. And so there's another statement that if you forget about the numbers, then this thing which I have just defined is just the same as barcode. And also I should mention that some similar ideas about the Brown numbers over Q appeared independently in the work by Lepetrug, Neer, and Viterbo at the same time in 2020. Okay, so that was the construction. So let me just recall that I have taken a function and a field as an input and constructed an enhanced barcode. So basically some picture like this on the right, the pairing and numbers. Any questions on the first two parts before I move on to examples? No questions?
Misha, you only consider the situation when you have only finite number of critical points. So it's
Oh,
possible to have
yeah.
infinite number.
Yeah. The manifold is compact without boundary.
I see.
Yeah. So yeah, only finite number of critical points. This all can be extended to manifolds with boundary, to cobordisms with ease, or alternatively, if the manifold is non-compact, then you have to assume some natural conditions like linearity at the infinity or quadraticness or at infinity or something like this. Yeah. Okay. So, well, in this case, if there are no questions, then I should, I guess, move on to examples. So the very basic non-trivial example. Yeah. So the point of all this is this numbers. Yes. So the barcode was defined way earlier, and our condition is the numbers. So I will be primarily interested in the properties of these numbers. So the first non-trivial example is RP2. There's a standard Morse function on RP2, which gives the standard cell decomposition, and two critical points of indices 1 and 2 are correspondingly y and x. Okay, so two classes. So the attaching sphere for x is one-dimensional sphere. It is again drawn in purple. The attaching disk for y is again drawn in blue, and the barcode for the standard function is drawn here. So x and y are paired with coefficient with Brown number 2, well, because the boundary of the Möbius strip is twice its middle line. Okay. Yeah. So similar. Yeah. Well, this is if this only holds of the characteristics of f is not 2. If it is 2, well, then the barcode is just 3 points, none of which are paired. And similarly, one can see that the standard Morse function on RPN gives you the barcode which looks like this. So we start with 0, with the, well, there are n+1 critical points of indices of all the indices from 0 to n, ordered by its index, and then the first and the second points are paired, the third and fourth are paired, and so on. So, for example, if n equals 6, then the picture is like this, and all these coefficients are 2, right? Okay, so the third example, well, it's not an explicit one, but one can find a function on S4, a certain weird function on S4, which over Q will give you the barcode, which is drawn here, right? So there's some explicit construction which allows you to construct such functions. Right. Then the property is, the first property is that the dimension of the homology group in the degree k of M over F equals the number of homological points of index k, right? So this explains the name, right? And this property also tells you immediately that this barcode, even let alone the enhanced barcode, just the barcode proper is does depend on the field. Yes, so depending on the field, the number of homological critical points is the dimension of the homology of M over this field. So surely, if you vary the field and fix the function, you will get different barcodes, but the points will be the same. So the points will be the same, but the pairs will be different. Right, so the point duality, and a nice little a pleasant thing, it tells in this setup that if M is orientable, then the enhanced barcode of for minus F is that for F turned upside down. Well, by upside down, I mean, well, literally you have to replace in all points of index k by index n minus k, and literally turn the picture upside down and the numbers will be the same. Okay. And then the next statement is that given any manifold M of dimension big enough, at least 4, and any lambda in any field which is either Q or FP, one can find a function on a manifold which has a pair with Brown number plus minus lambda. So as a trivial consequence, Brown number over Q may be non-integral, right? So for example, here this Brown number over Q is 1/6, which is non-integral, which is well, maybe a bit counterintuitive, like for some. And the slogan here is that individual Brown number can be any given in advance. So you give me the manifold, you give me the number in the field which is either Q or FP, and I give you the function which has at least one pair with the given Brown number, right? So in some sense, there's no control over individual Brown number. It can be any. Okay, so that's the end of the third part. Any questions on this third part? It does all make sense?
It does.
That's great. Okay, so then the baby version of the torsion theorem. So let me define a single number associated to the Morse function and a field tau, which of course stands for torsion, but that's the theorem. So this is the product. Well, this is the formula. So what's happening in this formula? So this is the product of all the Brown numbers on all the bars, with the only catch that I should take some Brown numbers to the power -1, depending on some parity. Yeah. So theta runs through all the bars. Lambda theta is the Brown number on the bar theta, and the degree of theta is just the index of the upper critical point, right? So depending on the parity of this index, I should take Brown number to the power 1 or -1, depending on this parity. Yeah. So that's why we call it this tau alternating product of all the Brown numbers, right? This is the torsion in general is the multiplicative analog of the Euler characteristic. Yes. So if you have, well, the Euler characteristic is the alternating sum of some generators of, say, simplexes, right? So you take each simplex with either +1 or -1, depending on the parity of its degree. So this is the multiplicative version of this notion, right? So you take the product, right, instead of a sum, and then you take and then you raise each term to the power +1 or -1, depending on the parity of the degree. Yes, so that's a perfectly fine analog of the characteristic torsion. The theorem now states the following. So suppose that there is no homology over F for all the K, there is no Kth homology over F of M for all the K from 0 to dimension of M, with endpoints excluded, then this number tau is independent of the function, right? So this should be compared with this slogan that individually Brown number can be any. You give me number, I give you the function. But somehow, if you take the product of all the numbers, they somehow cancel out, and the product is independent of the function. So that's the statement. So then there's actual question. Okay, so well, if this product is independent of the function, then how to define this product explicitly in terms of the manifold without appealing to function? So there is a natural answer to this natural question, which is given by this formula. So you have to take you have to take the orders of the homology groups of M over Z. Yeah. So what I mean by the order? Well, in general, homology is just is an abelian group, so it may have some torsion, but if this is assumed, then there's no free part, so there's only torsion part, so there's a finite group, so it does make sense to take the order here. So hashtag is the order of the finite abelian group. Then you have to take the this, so it is the order is the natural number or 0. Then you take its class in the field, and then you take the product of all these numbers in the field for the orders, and then this is this equals the product of all the real numbers, right? So that's the statement, the baby version. An example is RPN and Q, right? So we have this picture for RPN. There are, well, approximately n over 2 n divided by 2 bars, because almost all points are paired, right? The number of which the number on each bar is 2. So so then the example tells you that for if M equals RPN and F equals Q, then the tau is plus minus 2 to the power n divided by 2, where these brackets denote integral part. So the point is that this tau that this holds for any F, yes. So not only for this standard Morse function which I've been considering earlier, but just for any Morse function, any strong Morse function, right? Okay, so that was the end of the fourth part. Any questions?
So here you have a really strong topological restriction on HK being equal to 0. So for all k between 0 and dimension. So can you weaken this type of assumption and get something reasonable, or if you weaken it, it won't be reasonable at all?
I don't think
modifications.
I don't think that there's an alteration of the statement which weakens the assumption, because I mean if there's homology, then I mean I don't have any statement, but I sort of expect that if there's a homology, then generally you can find two functions with different tau, more or less. Well, I mean it's not a theorem, but I expect that the homology, the existence of the homology breaks down the statement completely.
I see. And can I ask you, like in general, if you, let's say, to take different fields, is there any like reasonable formula that allows you to go from one to another, like between these taus for different fields?
For different fields, not sure about it. So that depends on whether you consider this formula to be reasonable, yeah. So this brackets denote that you take the natural number and you consider it in the field F, right? And then you take the the inverse in this field. I think that's the best thing to say. So yeah, I mean, so if you know, yeah, if you have some integer and you know it's residual modulo 5, and then you forget the integer, and then you're wondering what is the residual modulo 7. Then I guess it's not possible to answer this question. Yeah, right.
Can I ask, so this restriction on the homology, so how rich is this class of manifolds that have no homology between 0 and top dimension?
Very poor.
I mean, yeah,
very
so
poor.
a sphere, I guess.
Well, yeah, the sphere. Yeah, well, I mean, it's more or less the same as homologous sphere. Yes. Okay. So homologous sphere, okay. F homologous sphere. Yeah. So so this class includes all the F homologous spheres. Yeah. So yeah.
Okay. Right.
But surely this condition is extremely restricted. Yeah. So for sphere, this is just yeah. So for sphere, this is just one. Yeah. For our RPN, this is this. Yeah, I don't think I can add anything. Sorry. Yeah. So, any more questions?
Do you have some honest computations, let's say, for some famous examples, like, I don't know, let's say, this Milnor spheres or something? Did you try it, I think? Or, I mean, maybe it's not.
So the only, so if M is a Z homologous sphere, right, then there is no homology over Z. Then this formula tells you that for any Z homologous sphere, tau is just one, right? So, right, for Z homologous sphere, this is just one. The order of the trivial group is just one. So for Z homologous sphere, like for Milnor spheres, right, this is just one. Or wait, what do we mean by Milnor sphere? I thought that Milnor sphere is a topological sphere, but it's the different smooth structure. Or do you mean
yeah,
the
so
compressed?
here it does, yeah, right. So this tau doesn't remember anything about, yeah, right.
Yeah,
so since they're all homeomorphic, then probably, yeah, taus will be the same. So this tau will not detect, so it doesn't really depend on the smooth structure, right?
Oh,
So
no. It's a pure topological thing. Yeah.
I see, okay.
Yeah. So essentially, I could have taken not F, not a function on the manifold, but simply it is enough to consider just say that maybe even drop the assumption for on a topological space to be a manifold, just a topological space which is filtered by topological subspaces, such that two neighboring topological subspaces differ in the homotopy sense by the attaching of a sphere, by attaching of one cell. Yeah. So if you filter your topological space somehow such that xk and xk is homotopy equivalent to the xk minus 1 with a single cell attached, then this whole construction works. Right. So the point here is that I don't know any reasonable way to obtain such a filtration other than from a Morse function.
Basically, if let's say you perform something like, I don't know, you have some manifold and you do, let's say, a single cell attachment, you can basically write down the relation between taus, right? Before and after the attachment.
Well, a single.
Yeah, I'm just talking about some basic surgeries that you can perform. So
yeah, well, so this will depend on the function, right? Because I mean, if you perform a surgery, then if this acyclicity condition was satisfied, then I guess it is hard for it to be satisfied after the surgery, and vice versa.
I see. Thanks.
No, I mean, I'm not sure about it, but I guess.
Yeah, I don't know whether it should be always true, but yeah. But I think it's quite reasonable to maybe investigate or to think.
Yeah, I agree. I agree. Yeah, thanks. Great. All right. So, any more questions? Okay. So the grown-up version of the torsion theorem is the following. So I need to have some preparation first. So let pi 1 is the fundamental group of M. So let rho be a one-dimensional representation of the pi 1. So the map from pi 1 of M or to GL1 of F, which is just F star. So the map from the group homomorphism from pi 1 to F star. Or in the fancy words, one-dimensional local system on the manifold. Given that, one can consider the twisted homology of M, yeah, the homology of M twisted by rho, denoted like this. Then second, given a function and the one-dimensional local system on M, F, and rho, I can construct. I mean, I'm not given the construction right now, but it's more or less essentially the same. One can construct the twisted enhanced barcode, right? So previously I was constructing just enhanced barcode. Then if there is a twisting, so which is aka one-dimensional local system, then there is a twisted enhanced barcode and hence twisted Brouwer numbers. So this is just the barcode, but so the critical points are those of F. So the critical points are the same, but the pairing and the Brouwer numbers may be different, right? So you can not only vary the field, you can also replace field by a representation of the pi1, and you can vary this representation of the pi1, and for different representations you get different pairings and numbers. So this enriches the above construction. But this time there is a greater ambiguity in lambdas. So previously lambda was just a non-zero element of the field defined up to sign, but now it is also defined up to the image of the pi. So pi is the same as pi1. So there's this image of this homomorphism, and the lambdas are defined up to subgroup, up to plus minus one, up to plus minus times the subgroup, which is the image of the of pi in F star. So similarly, I can define tau of F and rho, just the product of all the product of all the twisted Brouwer numbers with coefficients in rho, and in general, tau of F and rho does depend on F. So if there are no assumptions on the manifold, expectedly this tau depends on F. But so again, expectedly, here comes the acyclicity condition, which is the precisely the acyclicity. So if there is no twisted homology of M whatsoever in all the degrees, yeah, so the dot denotes all the degrees, then one can divide the Radmacher torsion of the manifold, denoted as tau r, which lives precisely in the same group, or in the same, say, quotient set. It is a topological invariant, a classical one. It can be used to classify the Landspace. Yeah, so the point here, the point being is that Landspaces are a certain topology, are certain manifolds which are many of which are homotypically equivalent but not homomorphic, right? So if the two manifolds are homotypically equivalent but not homomorphic, classical topological invariants are incapable of distinguishing them. So say like homology groups or homotypic groups are incapable of distinguishing them, and you need some finer invariant which will be invariant under, so it should be a topological invariant, so it should be invariant under homeomorphisms, but it should be, finer, and this Radmacher torsion is the example of such an invariant. And then, yeah, so the theorem, the grown-up version of the same theorem sort of says that, okay, so let rho be a one-dimensional representation. Suppose that there is no homology. This allows us to define the Radmacher torsion. Otherwise, the Radmacher torsion is not defined. And the theorem states that the Radmacher torsion of the manifold equals the product, the alternating product of all the twisted Brouwer numbers. In particular, this tau is again independent of the function. So here is the same inverse alternating product of twisted Brouwer numbers. So this tau, which was defined similarly to this formula, equals the Radmacher torsion, and the which is a classical invariant, and of course, so the Radmacher torsion itself doesn't have anything to do with Morse theory. It's just a part of just algebraic topology. So here M should not be need not be a manifold, even just some topological space within a cyclic local system on it gives you has the random saturation, right? So the reason why we call it with the ground-up version is that here this number, which is independent of the function, is sort of not that interesting because it can be expressed in terms of homology or f of m, right? So well, yeah. So this formula tells you that it's not, you know, something like radical in U or maybe not something deep, but the random saturation is a classical invariant, which is a useful one, right? So that's why it was kind of surprising for us to discover that in essence Barcode does carry some finer topological information, like random saturation. Right. So that was the statement. An example is the Landspace. So it is say the three-dimensional Landspace. So it is sort of manifold. I mean, I'm going to be brief here. It is a sort of manifold which depends on three integers p, q1, q2. Qi's are coprime to p. For field f, one has to take c. The row, yes. So the pi one of the Landspace is zp. So I should give you the map from zp to c star. And it is the natural one. So the generator in zp goes to eta, where eta is the primitive root, the primitive pth root of unity, non-trivial. Yeah. So that's this defines you the homomorphism. Then Ri's are just the inverses of the Qi's in ZP.
Misha, typically Landspaces have two parameters. Like, why is there, like, what's the relation between LP, Q1, Q2, and I don't know, LPQ?
Oh, maybe I could just give you the definition then. Yeah, will that do? So the definition is that
Yeah, maybe just my problem, but I used to, I know what LPQ means, but this three parameters, it's a bit more sophisticated.
Yeah, it's just a notational issue, right? So, so let me just give you the definition. So it is S3, which is in C2, and I quotient out by Z1, Z2. It should be equivalent to Z1 times eta, eta to the power Q1 and Z2 times eta to the power Q2, where eta is this thing. How does it sound?
It sounds good, yeah.
So this is L, P, Q1, Q2. Right. Yeah, okay. So then there is a standard Morse function on this lens space, which gives the standard cell decomposition in 4 cells of indices 0, 1, 2, 3. So if you don't twist the coefficients, right? If you just take the constant local system, say, well, just the constant C coefficients, then the barcode looks like this, yes? So there's homology in degree 0 and 3, yeah, over C. And that's it. There is no more homology. And but this barcode depends only on P. So it depends only on the fundamental group, and surely this is a weak invariant. As opposed to the twisted barcode, the barcode twisted by this one-dimensional local system, which so this is the barcode which sort of defined for the same function, yeah. So the function is the same, its critical points is the same, so the points are the same. 0, 1, often this is 0, 1, 2, 3, but now the it should be acyclic, right? It should be acyclic. So it means that there should be no homological critical points, right? So I recall that critical points, homological critical points, count the dimension of the homology in the corresponding degree. If there is no homology at all, there is no homological critical points. So all the critical points are paired, and there is only one way to pair critical points of these indices, which is this one. And the numbers are this. Well, there's just some random numbers and some complex numbers. And indeed, the Dartmouth torsion of the Landspace is just the product of all these numbers. No, the inverse or the product of these two numbers. Yeah, so that's the example. Okay, so I guess I have 15 more minutes, right? So
Yes, exactly.
let me, yeah. So any questions on this fifth part before I move on to parametric story? So everything is clear, yes?
More or less.
Okay, okay. Right, so then let me say a few words about the parametric stuff. So it is, well, it will only depend on the first like 3 or maybe 2 parts, yes. So I will not be talking about torsion. I will be just talking about the barcode, and I will not even twist the coefficients. So the whole story makes sense if you don't twist the coefficients, yes. So if you didn't get the 4th part or the 5th one or both, then it's all fine. So what's the setup of the parametric Morse theory, just in general, without any barcodes in mind? So now I have not a single Morse function, but a path of a generic path of functions on a manifold. So it is a map from M cross interval -1 to 1 to R, and the coordinate of the interval is T, which we think of time. So one can imagine the space of all the functions on M, and then there's a point which moves in this space, and the coordinate of this path is T. Then it is useful to depict this path by the serve diagrams. So the serve diagram of the path is the following subset of R2. It is the subset of the points TC, such that C is a critical value of FT. So I will give you the example a bit later. Well, so it's just a curve in R2, which looks like this. Then there is at finitely many times for a generic path, the function changes dramatically. And there are 2 types of such changes which are of interest to us. First, the birth or death of a pair of critical points. An example is ft of x. So the function is just on the real line, say ft of x equals x cubed plus tx. So this corresponds to a cusp and a serve diagram. So there are 4 of those. Yeah. So yeah. So this is the picture of how the function changes. This function changes. Right. So if t is less than t1, say, then there are no critical points. I mean, locally. Then there's at the point t1, the function is not Morse. That has a generally critical point, and then if t is equal, if t is greater than t1, then there are 2 critical points which arise. A classical picture. And then, since we're interested in strong Morse functions, where there's also another stratum, which is sometimes called the Maxwell stratum, which is that a function of ft0 is not more is Morse but not strong. So the two critical values collide, and this corresponds to a self-intersection on the serve diagram. And the picture, well, again, the same picture. So the example of this is this. Again, the function is say on the real line. Then, well, it's before this bifurcation, t the blue point is higher than the purple one. And then after the bifurcation, it's vice versa. And at t equals t naught, they have the same critical value, right? So this corresponds precisely to the cusp, to the self-intersection on the serve diagram. Here, t naught is this point. Sorry. Yeah. So the arcs of the serve diagram correspond to critical points, right? So this blue arc corresponds to the blue point. The purple arc corresponds to the purple point, right? And at this point, they have the same critical value. Yeah. So that's the classical statements. Now the question is now, how does the enhanced barcode change along the way? So okay, so we know how the function can change, and then we ask ourselves how the enhanced barcode can change. And then there's an answer. And in the case of the classical barcode, the barcode proper, so without numbers, it was answered already by Baranikov in his paper. And they is so what we did is we investigated how the numbers change. So the answer is, well, is twofold, which correspond like accordingly to two types of bifurcations. So in the first case, there is nothing much interesting going on. There are two newborn critical points, and they are paired by a bar with Brown number plus minus 1. So the picture is like this. There is a tiny bar which appears, and the number is plus minus 1. Well, in any field, yes, 1 is in any field. So that's okay. And then much more interesting case is the case number 2, where we have two critical points on the same level. And then there are several combinatorial cases of this, like if both are upper in the pair, if there is one upper and one lower, if one is upper and one is homological. So there are many, like five different cases. But let me they're essentially the same. So let me consider only in the case uppers. So both points which collide are upper in their pairs. Yeah, for now at least. So there are two types of bifurcations. First, the trivial bifurcation. The trivial bifurcation is depicted on the left. So the pairing doesn't change. So what is drawn here is the part of the serve diagram which corresponds to this. So this picture is this local picture of the serve diagram, right? Zoomed in. Right. So basically, again, nothing interesting is going on. The pairing doesn't change. Yes. So this point was paired was this one, and after the bifurcation, this point is still paired with its old pair, and numbers don't change. Ground numbers don't change. So it is indeed trivial bifurcation in any reasonable sense. And then there's a non-trivial bifurcation where the pairing changes. So for example, here. So here, let me say x, y, a, b. Yeah. So before the bifurcation, the point A was paired with point y. But after the bifurcation, the point A is paired with point x. Okay. And similarly, before the bifurcation, B was paired with x, but after the bifurcation, B is paired with y. Yeah. So the pairing changes, and this is what Baranikov has noticed. And the numbers also change, but in some fancy way. So if the Brown numbers were lambda and mu beforehand, before the bifurcation, then they can change, yes, but they change like this. So the one number becomes c lambda, and the other number becomes mu divided by c, right? Where c is just some number, a magic number. Or another example of non-trivial bifurcation is of upper and homological type. Yeah, so this is homological. This is upper, this is lower, right? So this is also possible. Yeah. So in this picture is slightly less interesting than this one, because well, the number can change in any way. Yeah. So it was lambda before, but bifurcation now it's c lambda, and there is no relation between the two. But here we see, here in this central case, we see that despite the fact that the numbers change, the numbers themselves change, the product of them doesn't change. Yes. So the product was lambda mu and is lambda mu like after the bifurcation. Yes. So how does it help us? Well, in the following way. So the rightmost, so we note now that the rightmost case doesn't occur under a cyclistic condition. Yeah, because again, the number of the homological critical points equals the dimension of the homology. If there is no homology, so the dimension is 0 in any degree, then there is no homological critical points. So if there is no homological critical points, then the rightmost picture doesn't arise. Okay, for any function. Yes. So I fix the manifold. If it satisfies this acyclistic condition, then for any function there is no homological critical points, so there is no picture like the one on the right. And this, if one collects all this together, assembles this together, this gives an alternative way to prove that this tau of f is sometimes sometimes independent of the function. So by sometimes I mean if under some acyclistic conditions, under some acyclicity assumptions, right? Because if all the bifurcations look like this, yes, then and at each time the product doesn't change. Yes. So if this bifurcation occurs, then there's just there is one there's one additional Brown number, which is 1, so the product sure doesn't change. And if this occurs, then the numbers do change, but again their product does not. Yeah. So this allows you to prove that. So this gives a sort of bifurcation analysis proof of the fact that tau is independent of the function. And in general, it is an incarnation of the general like philosophy in the Morse theory that if you want to prove that something that you define in terms of Morse function is independent of the function, like say Morse homology or something like this, and then you have two ways. And the first way is just to prove the statement directly by inspecting like this function, or there's a fancy like way in the spirit of Morse theory, which is called the bifurcation analysis. So in this way, if you have two functions and you want to prove that that some quantity is the same for both, then you connect them by a path, a generic path, and you want to track down how this quantity changes along the path. And if you are able to prove that along the path the quantity doesn't change, then this surely proves that this quantity is the same for two functions, for any two functions. Yes. So the second way of proving statements, the bifurcation analysis way, like appears in this context in this form.
The cyclicity condition cannot be weakened, right? In this case.
No.
Yes.
Yeah. So you see that like here you see that the product is being multiplied by c, where c is just some number, which we have no control over. Right. Yeah. So I guess my time is up. So thank you very much for listening.
Thank you very much for the great talk, Misha. Are there any questions, comments? Maybe I'll ask one extra question. So you have this really very nice story in the Morse situation, namely for Morse theory and barcodes that appear in the story. But can you imagine some, I don't know, some adaptation of the same type of methods, let's say for Morse-Novikov story or something like that?
Yeah, that's a good question. So there's a paper by Asher and Zhang. So they in GT, then they define barcodes over Novikov ring for complexes over Novikov ring. So this includes Morse-Novikov theory, Hamiltonian Floer homology, and yeah. So the paper is purely algebraic. So it is a non-trivial task to extend this barcode theory to account. Well, so here, so I wasn't using the language of complexes along the way, but because it is not needed to state the theorems. But if you want to prove the theorems, then you have to go to the chain level and play with complexes over Z, over F, and the interplay between all of them. So if you instead have not a complex over Z, but a complex over Novikov ring, then there is a procedure which is described by Asher and Zhang, which associates a barcode to this complex. So surely there's an actual question if there are any numbers on their barcodes. So yeah, this is a work in progress. I'm trying to understand if there is. Yeah, so that's well, I guess answers it.
I see. Thanks. Interesting. Any other questions? Well, if not, once again, so I would like to thank Misha for this great talk, and it was a pleasure.
Thank you very much
for
for having me.
Yeah.